Good morning, boys and girls, or afternoon, depending on when you're watching this. My name's Dr. Science, and we're here today, and this is Brian. He's going to be my helper. And we're going to talk about a different kind of engineering you may not have heard of, metrology engineering. Metrology engineering is the science of measurements. And all engineers have to make measurements, or be at least worried about making measurements as they design bridges and have to make sure that things are the right length and fit together. Would you believe that one of the most basic measurements you can make is on a teeter-totter in the playground? Have you ever sat down with you as a child on one end and your parent, who weighs much more than you, on the other end, and try to balance? Your parent will end up sitting on the ground and you'll be way high in the air. There's a way for your parent to balance out, and that is by leaning forward or moving closer toward the center.
So you're saying it balances when you move this over here, is that right?
That would be one way to do it, yes. That would move the fulcrum, we call that the fulcrum, down toward the parent until the beam balances. This is our version of the teeter-totter. Okay, and this is where my child is sitting on the end, and here is the parent that's going to move, and you'll notice that he gets closer, it tips one way. If he goes farther away, it tips the other way. But when it's level, when the pointer is down there, that's when it's level. We can actually use the measure of position for the weight there versus the weight here, and actually weigh what's in the cup.
Let's do it.
We now have a balanced situation where I have 2 pennies in this cup and 3 nickels in this cup over here. Because it's heavier, it has to be closer to the center so that it keeps the beam level. Okay.
And when this is level, that's pointing to the center line.
Yeah,
so
pointing to the center line. Now watch what happens. Look at the number that we have there. What number are we on there?
30.
30, okay. When we take 1 penny out, it's going to be off, so I have to move this one closer to equal the weight of a single penny. What's the reading now?
It's about 37 or so.
Okay.
Yeah.
So between 30 and 37
yeah.
is equal to the weight of 1 penny.
Mm-hmm.
Okay. That's 2.5 grams. That 7 centimeters represents 2.5 grams of weight. We're going to repeat an experiment that was performed 2,200 years ago by Archimedes, an early scientist in Greece. The story goes, the king wanted a new crown made, and he had some gold available, and so he weighed the gold very carefully that he had, and he gave it to a craftsman to make a new crown. And when he got the new crown, he was suspicious. He was worried that maybe the craftsman had stolen some of the gold and replaced it with some other metal. So he was careful to weigh the new crown when it came back against the amount of gold that he'd given the craftsman. And sure enough, they weighed the same, but he was still suspicious. So he asked Archimedes, is there a way without scratching or damaging the crown in any way, is there a way to tell if all of the gold is back in the crown? Well, Archimedes thought about it a long time. As he was puzzling over it, he was sitting down in his bathtub and the water overflowed, and he said, Eureka! I can measure it by measuring the displacement of the crown in water and see if it's the same volume. If it's the same volume, then it's all of the gold.
So you're saying that if you got a bathtub filled to the top and you get in it and you completely submerge yourself in it, an equal volume of water leaves the bathtub, spills over the edge.
That's the way the story goes, yes. Mm-hmm. But 1,800 years later, Galileo had heard that story and said that wouldn't be an accurate enough way to measure it because of surface tension on the water. We can talk about that a little later. We even have an experiment for it. But so Galileo put together the experiment that he was sure that Archimedes had used, and that's what we're going to repeat here today. Here we're using pennies again to be our weights. We've got a sack of pennies over here and a sack of pennies over here, and they're in perfect balance. So how can we tell if they're the same composition inside, have the same volume? So I've replaced one of the bags of pennies with my cup with coins in it again, and I've slid it back and forth, and I've got this one now balanced and level, okay? Now comes the interesting part, and the part that Archimedes did, where we're going to use the cup of water and bring it up until it covers just the pennies. We don't want to go beyond the pennies. And as you notice that the beam unbalances because the pennies are trying to float in the water. Now I'm going to have to bring this cup up. Okay, we now have the pennies all the way underwater and very little else. And what is our reading over here?
Looks like it's about 8.5 to 9.
8.5 to 9 centimeters, okay? Mm-hmm. Now we're going to take that one off and weigh the other one. Notice that one's got a green band around it. This is the blue band. And see if this bag of pennies, which we know weighs the same in the air as the other one, see if it weighs the same in the water.
That's somewhere around 10, it looks like.
Okay, 10, and the other number was what?
8.5 to 9.
Okay, so we've got about 1 centimeter to 1.5 centimeters on the movement on this one to balance it with that. They read different, which tells us that the number of coins in the two bags must be different, even though they weighed the same. So this would be how the king could tell that some other metal had been used in his crown. The reason we have the problem here with the pennies is because pennies made after 1983 are less copper and more zinc. They're lighter weight than the older pennies, which were nearly all copper. So what we have is 8 of the old coins weighing 3.1 grams each to 10 of the new coins weighing 2.5 grams each. But what we just measured was the difference in the volume in water. And that's how we can tell that there's different material inside. So now we're going to explain why Galileo thought that the bathtub story wasn't accurate enough for measuring the crown.
Sticky water, right?
Sticky water.
Yeah.
If you look closely, you see the water is near the top of that cup. The question is, how much mass can I add to the cup in the form of pennies until that spills over? And we're going to add them one at a time. Take a while to get, whoops. Okay, now you can, if you look carefully, you can see that there's a curvature on top and the water is actually higher than the edge of the cup. And we still haven't had anything spill out. So by the time it spills, we won't have any idea of what the volume of the cup was at the level.
Well, I kind of counted. You have almost 30 pennies in there.
Yeah.
And it still didn't leak any water off the top.
That's right. It didn't bring any water out. So you can put a lot in there. Now the question is water always work that way?
Oh, what would change that?
Well, if you add soap to it, you reduce and you would in the bathtub, of course, then it would flow more easily.
Well, do you have some soap? Can we drip some soap
We
into
can
that?
try that. Let's put a couple of drops of soap in it and see what happens to that. So we've pushed this about as far as we can. You see we've got a very high meniscus, we call it, with the water above the rim of the cup. And now I'm going to add my soap, which should break down the surface tension. Oh, look at that.
Look at that.
Oh.
It just collapsed.
Yeah.
Wow.
So the difference, the water that's now out here isn't weighing telling us how much displacement we occurred with the pennies. It's only telling us how the water was sticking to itself.
So
That's called surface tension.
And this makes for an imperfect volume measurement.
Yeah, we can't make the volume measurement that we made as precisely with the beam a while ago. Okay, well, thank you for your attention today as we learned about making measurements and how they've been made for many thousands of years, actually. Something you can do at home is maybe try your own version of this kind of experiment with floating things in the bathtub and seeing how the water rises, or doing it in a glass of water. The other thing you can do is, now that you're thinking about linear measurements, which is like what we're doing with the yardstick, is make yourself up a paper scale to hang in your closet, to where you can write on it every now and then and show your growth rate. Put a date and your height on a scale that looks like a couple of yardsticks. Thank you.